So this is the first in a series of videos demonstrating some of the modern graphics techniques that we're doing in class. What I'm going to do is start by generating the simple hello world triangle, and I'm going to do this in modern OpenGL, Vulkan and WebGPU. And in particular, this is to show some of the differences between the APIs. Predominantly, we're going to focus on either using OpenGL or WebGPU, but you have the options to choose what you like. Now, WebGPU and Vulkan are very different from OpenGL in the fact that they're not managed. So some of the code in particular is only relevant to OpenGL. And we'll start with that here. So what we've got here is the file opengltriangle.py. When we run this, you will see that it just generates a simple hello world red, green and blue triangle. And this starts in main here, so I've got if name equals done to main. First thing we need to do with PySide, because we're using PySide to create, in this case, our OpenGL context, but also the window that we're going to render into, is to set the OpenGL version. Now, modern OpenGL is version 4.5 or 6 is the maximum. On the Mac, the highest we can support is 4.1. I'm running this on a Mac, so I tend to sort of set it to this level. And what this does here is it sets the default OpenGL surface format so that we have a major version of 4, a minor version of 1, and we have core profile. This is modern OpenGL that uses shaders and uses proper graphics pipelines, unlike OpenGL 3.x, which is the older deprecated immediate mode OpenGL. So we set this default surface format. Basically any windows that we create will always use this. For some reason I had that doubled there. Next, I will go back over this a bit later, but basically I've got a command line argument here, just checking to see if we've got debug passed in, because we're creating a queue application. Unfortunately, queue application captures any exceptions that are thrown and tries to manage them nicely, which when we're trying to debug OpenGL issues can be problematic. So basically, if we're not running in debug mode, which is the default, we'll just use a normal application. If we're trying to figure out why our code isn't working, we're going to run this debug application. And basically all that does is it writes a hook that will grab the notify and then print a traceback of any exceptions that come through. So this just helps us when things go wrong when we're debugging. And all of my code basically has this built in for development purposes to start with. And then finally, we're going to instantiate this main window class, resize it, show it, and pass control to PySide, or Qt. So this is the simple part of it. Now, this window itself inherits from QOpenGL window. QOpenGL window is a full window, as you can see here, that has a full screen OpenGL widget placed inside of it. And it implements some core functionality to do with how OpenGL works. In particular, it implements initializeGL, paintGL, and resizeGL. Each one of those are where we have to put specific code to get our programs to work. So dunder init in this case does very little. It calls the parents initializer, it sets the title for our application. What happens next is that the first time that paint is called, a flag is checked internally to see whether the OpenGL context has been initialized. If it hasn't, then initializeGL is called once the context has been initialized. So this is called once when the OpenGL context is created. And this is where we do all our initial setup. So things like creating our buffers, creating shaders, doing any sort of initialization setup. So first call should always be to make the current OpenGL context active in this thread. I'm setting the background color. I'm enabling depth test, multi-sampling. I'm now creating a triangle, which I'll go through, and then I'm loading shaders from strings, which I'll go through. So create triangle, basically I have a pile of vertex data here which is in the form of NumPy array. I've got the x coordinate, the y coordinate, the z coordinate, and then I've got the red, the green, the blue value. So basically bottom left red, top green, bottom right blue. We then go through, and OpenGL uses this process called vertex array objects to store vertex data. Effectively this gets past GPU side to be processed later. So what we've got here is we're creating a vertex array, we're binding that to make it the currently active one, so any subsequent calls to OpenGL functions will work on this buffer. And OpenGL uses this bind to edit metaphor for all of its buffers. So we create a buffer at some stage. Whenever we want to modify or update it, we have to bind it to make it the currently active buffer. And only one buffer can be active at any one time, which is one of the key differences between OpenGL and the other APIs, where they can work on individual buffers and we can manage the locking of that. So what we're going to do is we're going to generate a vertex buffer. So in this case it's a GL array buffer. So we generate one buffer. OpenGL will allocate an ID to this. We then bind this to make it active, and then we've got the command here GL buffer data, and what that will do is it will pass across this vertex data to OpenGL. We've given it the hint here to say that this is to be used for drawing, and it's static data. It won't change that much. Next, we need to tell OpenGL how this data is formatted and how it's going to appear as part of the input to the shader. And this is what GL vertex attrib pointer does here. Basically, you can see here it's giving you all the information about each of the elements here. So basically, this is saying that input 0 to the shader had 3 components of type float. Whether or not this should be normalized, this is how big the data is. Now this is important because this is in bytes, and obviously in Python it gets a bit more complex that we don't tend to deal in things with bytes and things like that. But vertex data.item size will give us basically the size of an MP float, which is 4 bytes. So this will give us 4 bytes, and then you can see here we're saying this is multiplied by 6, and that's basically saying to get to the next block of data you need to move 1, 2, 3, 4, 5, 6 floating point values to get to the next block. And most graphics APIs use this idea of how is my data structured, how do I offset into that data. The next one here, and again this is a bit more complex, we're using the C-types Python module. So basically this allows us to use C-like data structures and C-like ideas within Python. And the reason we need this is because OpenGL is a C API, and we need to communicate in terms of OpenGL understands. OpenGL wants to know how far into this array of data it needs to move to get different things. In this case we're saying this is a void pointer, so basically we're saying the memory starts here, and in this case we're saying at the beginning of the buffer. Now next we'll enable this vertex attrib to say right, this one's active, use it. We do the same here, and this is where these buffer offsets come into play. So same thing again, we've got input 1 to the shader, has 3 components of type float, no need to normalize it. To get to the next chunk of data we need to skip this size of 6, so again same thing, so here we've got 6 floats here. If you want the next one it's another 6 floats. But now we also need to say in this case how to, within this row of data, do I access the component which is the ones I want to read, these 3 which represent the color. And in this case it's going to be 1, 2, 3 floats offset from the beginning of this row. So this calculation here is saying vertex data.item size, so that's the size of a floating point, 4 bytes, multiplied by 3 because it's the x, y, z we need to go across. We're then going to activate this to say that this shader attribute is needed, and then we're ready to go. Typically we'll bind vertex array 0, which is basically to turn off anything that we've just created, because a lot of the time we'll be creating lots of these up front and then reusing them. Now the next thing is we need a shader to be able to render our scene. Now in this case the shaders are stored as a very simple string. So you can see here, this is what I call vertex shader. This is the input to our pipeline. And in this case I've said my data is laid out, location 0 has a vec3, and I want you to call it in position, and input 1 is a vec3 and I want to call it in color. So that responds to that data structure that we created earlier, and all this is going to do is it's going to pass on the position. So the output of the shader here is GL position. That's mandated by OpenGL. That's what gets sent to the rasterizer later to be turned into pixel data to be colored in. And then we're passing out also this vertex color, and that's going to be the color that's been input. This then comes to the fragment stage here. The fragment stage receives the vertex color, which is interpolated in a perspective correct fashion, and we set the output color, i.e. what color should I put the pixel here, to be this input color. And so what you see here is, while we've got red, green and blue cropping up here, if we're at that pixel, the first vertex, then it will be all red. But as we gradually move across, what we're doing is we're interpolating this way red to blue, we're interpolating this way red to green, and we're interpolating this way blue to green. As we go across, whatever that color is gets interpolated across, and that's what gives that colorful thing, because they're interpolated. If we were to modify this, and instead of out we have flat out and flat out, and we run this, oops, I got that wrong. That should have made that sorry, that one, that's what I got wrong. It will pick up the last color, so no interpolation happens. So you can see that interpolation is because the default behavior of outputs to inputs is to interpolate the values. Now to load the shaders, we basically create a shader program. So the program is the overall program that's running on the GPU that fits into the pipeline to render. That is made up in this case of two stages, a vertex shader and a fragment shader. So we create a vertex shader here, we add the source from the string that we created, we compile the shader, check to make sure that compilation was a success, do the same for the fragment shader, apply the source, compile it, check that it was a success. We attach both these shaders to the program. The order that this happens is pretty flexible as well. So you can create two shaders, you can compile them, then you can attach them to a program, and vice versa, and so on. After that, there's a linking stage. The linking stage basically takes these elements here, links them together, make sure inputs and outputs match, and then this will give us a program. We can then activate that program to make it the currently active shader, and in this case I'm deleting both the shaders because I no longer need them. Now every time we need to render, PaintGL is called. In this case I'm setting the viewport, so that sets the width and the height of the screen. I'm clearing the screen, I'm clearing the color buffer, so basically that clears any pixel color that's in there to the background color that we set earlier, and the depth buffer, so that resets that to the maximum depth. Then we say bind the vertex array. What that does is it activates that batch of data that we created previously, and then finally we call GL draw arrays, and in this case I want triangles, I want to start at the beginning of the buffer, and I want to render 3 vertices. Now this will change depending on context and what we want to render. So for example, lines, if I want to render in lines, you can see that I've got only one line there because I've only got enough data to draw that. I can do points, P-O-I-N-T-S, create GL points, and it's hard to see there, but there will be 3 points. You can just about make that one out, so tiny, and so on. In this case, we're just doing triangles, and then that's how we get our triangle. The final thing, which isn't really used in this demo, is when we resize the screen, we can get the new width and height and use that to do stuff. We will look at this in more details when we do more complex 3D work. In this case, it's very small. We've also got key press event, which is when we press the keys, it will do things. In this case, the only thing I've got is to enable wireframe as solid. This is very specific to OpenGL. Other graphics APIs do not let you modify the pipeline easily in this way. You have to create dedicated pipelines to do so. And that's it for this demo. We will now look at exactly the same processes, but in both Web GPU and Vulkan, and you'll see how much more complex both of those are.